Okay, so let's get started. The recording on? Okay, all right. So let's get started. I think I want to start a couple minutes early just to see if there is any questions about the lab that is due today. Anything we can answer. I hope that you've gotten most of your questions answered, but I'm happy to answer any last minute questions. Anything that has come up? Okay, so there is one. We have 2 office hours today because it was a lab deadline. So we had one just before class and there's one just after class. So if you have anything, just go to one of them or ask questions on PRZ. Okay, so we will get started with distributed transactions today. Okay, so this is a new topic that we will start. We were talking about clock synchronization. We talked about logical clock. We talked about vector clocks. We covered and then we talked about distributed snapshots. We covered quite a few topics already. This is one of the last ones before we switch to a new chapter altogether. Okay? So we'll talk about distributed transactions. You'll also see how locking is done in the context of these distributed transactions. That will give you some flavor of how locking is implemented in distributed systems. We talked about some of that last time. Okay, so this one, the emphasis is more on transactions, but we'll talk about locking in that context. We'll talk also about concurrency control and locking again in that context as well. Okay? So let me give you an introduction to transactions. If you've taken a course on databases, this should be familiar to you. Okay? Here we are concerned about transactions simply because in a distributed system, this is a more complicated problem where a set of processes may need to actually lock something and make some atomic operations on it. So transactions are more than locks. They give us better properties, as we will see, than just locks do. They give us an atomicity property, but it should be clear why we are even talking about it. Because in the context of distributed systems, this will give us lots of useful properties, as we will see shortly. Okay? But let's start with a very quick overview of what are transactions. You probably know this term from the database world. Okay? So essentially, they are a higher level mechanism for providing atomicity to computations. Okay? So what does that mean? Let's take an example here. Okay? We'll take a banking example. Assume that you have a bank application that has a bank database. Okay? There are 3 accounts in this bank database, A, B, and C. The balances on those accounts are $100, $200, and $300. Okay? And we'll assume that you are performing 2 operations at the same time on this database, okay? 2 concurrent operations. Okay? You client 1 is going to transfer $4 from account A to B. Okay? And client 2 is going to transfer $3 from account C to B. Okay? So effectively, okay, the account B is getting $7 total from clients 1 and clients 2. Okay? Now, if you look at that, sounds like a straightforward operation, but if you look at how this is actually going to work in a database context or even in a web application context, here is what you will have to do. Okay? So this is a table that shows you all the operations that actually have to occur in that database for this transactional. Well, so far we don't have transactions for these operations to succeed. Then we'll see why we need transactions in order to make that happen. Okay, so let's look at client 1's operations. So the y-axis here going down is time. Okay, so client 1 is going to first, because client 1 wants to transfer $4 from A to B. That basically means you got to read A's balance, that's 400. Then you take $4 out of that account. So then you write, okay, $4 or -4. So that means the balance is now dropped to 96. Okay. Now client 2 is executing their operations at the same time. Okay. So these are 2 parallel queries on a database, if you will, or 2 parallel set of operations. So you can't actually assume anything about the order in which these operations take place. So maybe the process that was running client 1's query, okay, finishes its time slice, or the thread that was running client 1's query finishes its time slice, and the system starts executing client 2's thread. Okay, so now client 2's query starts making progress. So 2 is going to read C's balance, okay, which is 300. So take $3 from there, it brings it to 297. Okay, now let's say you context switch the time slice for two ends. Somehow at some later point, okay, you switch back to the thread or the process running client one. Okay, so client one is going to continue. So it's going to read B's balance, okay, which is 200, and maybe the time slice ends. Okay, and you switch back to client two, is going to read B's balance is 200, going to add $3 to it, which is 203. And then you switch back to client one. So already read B's balance is 200, and then you write 204. Okay, so do you see the problem with this interleaving? Okay, so you essentially overwrote, client one has overwritten client two's result. So instead of B getting 207 as its balance, you are ending up with 204. Okay, that's an example of a race condition. Okay, you should have realized that the database is a shared medium. So in this case, we didn't talk anything about locks. We are just letting clients one and two execute whatever operations they want on the database. Normally, you would have locked some records or the entire database for this not to happen. But at least you should understand in the absence of lock what will happen. Okay, the same kind of race conditions can occur if you have threads. Okay, this is why in all of your labs we make sure that you actually implemented some sort of locking, because without that, anything that's shared, if there are two threads reading or writing, you will end up with problems like this. Okay? So in this case, the database is left in an inconsistent state. Okay, so what can we do here? So in database world, there is something called ACID properties, okay, that databases and specifically transactional systems that run on databases guarantee you. Those properties are good for us as well in distributed systems, but let's try to understand what those mean. Okay, ACID is an acronym. Okay, A stands for atomicity. Okay, atomicity or atomic operations means all or nothing. Okay, whatever set of operations you are performing inside, let's say, transactions, either all of them succeed or none of them succeed. You will never have a case where two of the four instructions are succeeded and the other two are not, haven't succeeded, or other two are actually you time out or you don't execute them. So you get this all or nothing property. It's like a critical section, but with a stronger guarantee, yeah, that either you execute all or you execute nothing. Even if the transaction is executed, half of the statements within the transaction and something happens, you have to undo its changes, okay, as we will see, to get our all or nothing property. Okay, so that is atomicity. Okay, second one is consistency. That says that if your system is in one consistent state, if you perform a transaction on it, it will go to another consistent state, which you make a transition from one consistent state to another. So you are never in a consistent state when you go from one transaction to another. Okay, so we'll assume so transactions will give us that guarantee because of atomicity and other things. Okay, so that's called consistency. Okay, isolation essentially means that effects are not visible to one another. There's another term for isolation, which is also called serializable. Okay, so what this effectively says is, even though multiple clients may be accessing and modifying the database all in parallel or concurrently, okay, the effects, the overall effects of this execution looks like each of them executed one at a time in isolation. Okay, so with 100 transactions all executing, okay, and you look at what state you are left at the end of that, okay, you will be able to arrive at that state because there'll be some order in which you can execute them one at a time without the other 99 executing at the same time and still get that. So that is called serializability. Okay, so even though your concurrency, the effects are as if you ran them individually one at a time. Okay, this allows you to reason about correctness of the system. Okay, so that is called the I, isolation, or that's the I in ACID. And D, which is durability, says once a transaction finishes and writes its changes to disk, there is no going back. You cannot undo at that point. Okay, so as soon as the transaction commits, very specifically, once the transaction commits, it says it's done. Okay, you cannot undo it at that point. But until it commits, you can undo all of its changes. Okay, so the changes are not durable. Once a transaction finishes and commits, that's it. Okay, you are essentially tied to whatever state it has left the database in. Okay, so those are ACID properties. We'll look at some facets of this today. This is kind of largely database material, but something for us to understand. Okay? But if you get that, get those properties, this is essentially what the previous slide will look like. Okay? It will look like, so that this is specifically the serializability property of ACID. Okay? It will look like even though clients 1 and 2 are actually executing in parallel, okay, the end state of the database looks like they executed sequentially in some sequence. Okay? In this specifically, you will see that it looks like client 1 executed, it moved $4 from A to B, you got 204, and then it looked like client B executed, and it essentially took B to 200 and so on. So you'll essentially get, it will look like these two have executed one at a time, even though they are interleaved. Databases will guarantee that. Or rather, transactional systems in databases will guarantee you that because of ACID properties. Is this clear? Okay. So with that background, let's now talk about more distributed systems, and we'll start thinking about how to make the notion of a transaction distributed. Okay. Transactions have been around for decades, okay, but largely for databases that run on one machine. Here we are taking that idea and saying, let's make them more distributed so they actually can work across machines or across databases and so on. Okay? And let's look at some examples. Okay? So the first thing is, very briefly, I'll talk about transaction primitives. The way you actually take a set of operations and make them atomic is you insert a begin transaction and an end transaction. Okay? And then anything in between is executes as if there's one atomic unit. Not unlike locks, where if you say grab a lock and release a lock, everything between that is a critical section. Okay? But critical sections are not atomic. Here you can think of the transaction giving you a stronger property. Either everything between the begin and the end executes successfully, or at the end of it, it looks like nothing has actually executed at all. Okay? Even if there's partial execution, databases will undo its operation, so it will look like the transaction never even executed on the system. Okay? So you need to have begin and end, and then in between you may have to abort the transaction, which means that you will kill the transaction, it will undo its changes. Okay? And then you can have reads and write. Transactions do make changes, so you will have read or write within that. These are the key operations we care about. Okay? And we'll come back to those, but let's take an example of where you might use a transaction. Okay? So airline booking is one example. We'll have travel booking as some of our examples today. So let's say you want to book a flight from point A to point B, okay? But there is no direct flight from A to B, so you have to go through one or more stops in between. Okay? Your booking as a whole should succeed if you have actually a confirmed reservation or a confirmed booking on all segments. Okay? If you get a booking on 2, but the third flight is sold out, that's not a travel booking because you can't get to your destination. Okay? So it has to be either all or nothing for this case, which is what you can do with a transaction. So this is an example of an airline reservation where you begin transaction. Then you say you make a booking or reserve from New York to Paris. If that doesn't succeed, you abort the transaction because you can't finish the booking. And if that succeeds, you go to the next statement saying book from Paris to Athens. If not, you essentially abort, and then you say Athens to Delhi. If all of them succeed, then you actually have a booking from New York to Delhi in 2 stops. Okay? So this is an example of all or nothing, because it makes no sense to just get some of those segments, but not all of them. Okay? Now we'll try to make, this is not a distributed database, it's just one airline's database, but now let's try to make this concept a little more distributed. So we'll start thinking about what does it mean for a transaction to be distributed. Okay? So we will essentially look at 2 concepts. One is called a nested transaction. Okay? And the second one is a distributed transaction. Okay? So a nested transaction is one where you have a transaction over 2 independent databases, but you still want your all or nothing property. Okay? Very simple example. Again, we'll go back to the travel example. You want an airline booking and you want a hotel booking. Okay? If you only have one of those 2, your trip is not going to work. Either you can't travel or you can't stay at a hotel if you travel. Okay? But these are 2 different companies which have 2 different databases. Okay? So there's an airline database, okay, and there's a hotel database. Okay? The booking on each of these databases is a transaction. You may have a transaction on your airline booking and your transaction on your hotel booking. Okay? So these are 2 transactions, but you want to envelop those 2 transactions into a bigger transaction, okay? Which is why these are called nested transactions. There are 2 transactions. or in this case listed as a sub-transaction. So your begin transaction and end transaction, and there are two smaller transactions in them, an airline booking and a hotel booking. Okay? So you want the whole thing to succeed, and you want each of the individual transactions to succeed. This is just nested, but now you see that this has already become distributed in some way because the transaction is touching two independent databases. Okay? That's one example of how you will use this in a distributed system. Is this clear? Okay. Here's another example. Okay. Now assume that you are back to the airline database, but the database has become very large. So you can no longer store it on one machine. Okay. So the database itself is now stored on multiple machines. Okay. So that think of this as one of those databases. Let's say it's an airline database, but because the size of the database is large, the database is split across machines, could be replicated, but let's just say it's split. Okay? Maybe one part of the database handles bookings from North America and Europe. The other part of the database handles bookings in Asia or something along these lines. Okay? Now, again, to make this transaction on the airline database, you might have to do a sub-transaction on the first logical database and the second logic. So this is just looks like one big database, but internally there are actually two machines that hold some of the data. Okay? So again, two sub-transactions, okay? On each part of the database, there is a distributed transaction. Okay? So we are more concerned in this class about the second scenario, not about the first scenario. Okay? This is also distributed, but we are mostly going to talk about larger databases that don't fit on one machine, that may be replicated or that may be distributed, and we want to implement transactional support on this system. Okay? So the idea is to take what we know about databases in the centralized world, which is something that a database class covers, and then try to see how to generalize this to a distributed world. Okay? The ideas we present here are not specific to databases themselves. Distributed transactions could be written even for, let's say, your web application and other kinds of things that you write, okay, in part of this course. Right? So the ideas are more general, but we will talk about them more from a database example standpoint. But you can use transactions even if you don't actually have a database. You just want to protect a set of instructions, okay, in your application and give atomic properties. Is that clear? Okay. All right. So we'll talk about two ways to implement the asset properties, specifically the durability property. Okay? Because remember what did I say? Okay? Once a transaction commits, its changes are actually permanent. You cannot undo them. Okay? But that also means that while the transaction is executing, there is some chance the transaction may not complete or commit and it may abort. So you have to have a way to undo your changes. Okay? So if you just have a file and you keep writing some new data to a file, and now you say, let's undo those changes, you won't know what to undo. So you have to keep track of what the transaction is doing in order for you to undo things. Okay? So this makes the storage systems for databases a little more complicated. And I'll show two examples of how you can implement this undo logic. Okay? The first implementation is called private workspaces. Okay? So logically, way you want to think about private workspaces is every time a new transaction starts, okay, we make an entire copy of the database, okay, and we give that copy to that transaction. Okay. The transaction executes, it makes some changes to the database. Okay. Now, if the transaction wants to commit, all the changes it makes to its copy of the database are then merged back to the original database, and then the changes are permanent. Okay. On the other hand, if you want to discard the transaction, abort the transaction, all you have to do is delete that copy, and you never made changes to the original copy. So there's nothing to really undo because you never applied the changes to begin with. So you're tracking the changes in a separate copy. Okay? Not unlike source code control system in GitHub, you can make a branch, you can make changes, you can either discard the branch or merge the change. Once you merge, it's not easy to undo it. Okay? You can in GitHub, but in databases you cannot because they are supposed to be permanent. Okay? So that's how private workspaces are going to work. Every time you have a transaction, make a copy, make changes to that private copy. Okay, that's why it's called a private workspace. And the transaction commits, merge the changes, otherwise throw away the change. Okay? Now you can imagine that there's a problem with this approach. Okay, what is the problem? Yes. Database is huge. And memory. Okay. So essentially, if you have a large database, okay, you will need a lot of, first of all, making a copy is not going to be cheap. Okay, let's say your 100 gigabyte database. Every time a transaction runs, you're going to make a copy of 100 gigabytes. Maybe the transaction modifies 1 byte of the data. Because you made this huge copy, you made one tiny change, and you merge it. Lots of extra work for that's going to add a lot of overhead to your system. Okay? So you need very efficient ways to make copies, okay? Which is what you need for private workspaces, because making a real copy not going to work in practice. Okay? It's going to add a huge overhead because there'll be lots of transactions. Okay? Every time if you start making these huge copies for large databases, it will not scale. Okay? It will become a bottleneck. Okay? So what we will do is we'll essentially make what are called virtual copies. Okay, so if you remember when we talked about virtual machines, I introduced this notion of a snapshot. Okay, a snapshot, and we'll use the same concept here. Okay, so essentially the database copy that you make is a snapshot of the database. Okay, because it essentially has the same contents as the database when you start, and then when the database or when the transaction starts making changes, the copy will start diverging from the original. But there's an efficient way to make a snapshot, which I had introduced as a virtual snapshot. Okay, virtuals, and we will use that exact same idea here. We'll make a virtual copy. Virtual copy means we'll not copy even 1 byte. We'll essentially copy the index and have the index of the database point to the same data. Okay, and here it is shown pictorially. This thing here is a disk. Okay, you essentially have a database with 3 records, 0, 1, and 2. And there is an index here, and the index is essentially pointing, this is essentially block 0, this is block 1 and block 2. So that way, if you want to get to any block, you go to the index, and then you go to wherever the data is stored. Okay? Now, to make a virtual copy, we will just replicate the index, but we will not replicate the data. Okay? So we will essentially make another index here, and those pointers will point to the same original data. Okay? So that's your virtual copy. You just copied the index. In the real copy, you will make an index and you will make a copy of these blocks, and the new one will copy to complete, will point to new blocks. Okay? In a virtual copy, the index is pointing to the same 0, 1, and 2 blocks. Okay? With one difference, now that the database is being modified by the transaction, the private workspace also starts getting modified. So let's say the transaction writes to block 0. Okay? You cannot write to the original block 0 because that is supposed to belong to the database. You have to write to your copy. Okay? So this is where we'll use what is called copy on write, okay? Which is what virtual snapshots do, where we'll make an actual copy at that time of block 0 and then write to that version of block. So you will see that now this private workspace points to 0 prime. Okay? The original index is pointing to 0. The original database is unmodified, it's still pointing to 0, 1, and 2. Okay? Whereas the private workspace points to 0 prime, 1, and 2. If you look at the pointers, you'll see that the first one is now pointing somewhere else. Okay? And then maybe you append a block to the database. You write to the end of it, then the private workspace gets a new block 3 prime, which is not there in the original. Okay? You will see that blocks 1 and 2 are still common to both copies because they have been unmodified. Whatever is modified, you make copies only on demand. Okay? This is far more efficient, because if the database transaction is modifying a small part of the database, okay, you only create copies for the changed portions, and the rest of it is the same. Okay? This is essentially the way snapshots work. Okay? In fact, if you actually see, your Mac OS actually has the file system, has snapshot capability. Okay? You can take a snapshot and it will preserve the copy of the file system as it existed at that point in time. And then if you keep making changes, it essentially uses copy and write and starts making new blocks. Okay? This is how Time Machine on Mac also works. Okay? You can go back in time because it's keeping snapshots of your disk as it existed in the past. Okay? So you can have multiple snapshots at each point in time and so on. Okay? So in any case, so this is the private workspace making changes. And now if the database transaction wants to commit, you have to merge the changes. Okay? So which means that 0 prime and 3 prime have to go back to the original database. So you will see now that the original database index has block 0, which is actually pointing to the modified block 0, which we call 0 prime here, and then a new block 3 has appeared. So now you see that the database has been merged with the private workspace, and the changes are now visible. At this point, you cannot go back. The database transactions committed. Until you had this workspace, you could have just thrown it out. Okay, and the original database is as is, so you didn't have to undo anything. Okay? Once you actually merge, you cannot go back. That's your commit. Okay, yes, question. Okay, question is, why does the private workspace have index 1 and 2 when it's not being modified? The private workspace is a copy of the entire database. That's what we said, right? Our original idea was, when you have a transaction, make a copy of the entire database. Okay, because a transaction might read data. It doesn't mean it only modifies, right? You can read some, let's say, records and do something with it. So you have to have access to the entire database, whether you modify it or not. So which means that you have to have access initially to 0, 1, and 2. So 1 and 2 you still need access to in this case. Okay? So the index has to point to all of the data in the database. Okay? The unchanged data and your changes. Any other questions? Yes. Okay, question is, when we implement this, do we have lock on the entire transaction or only in the commit steps? As of now, we have not brought locking in. Okay? We'll get to concurrency control in a few slides. Then we'll bring locking into this picture and see how to add locks to this. This is just saying, how am I going to implement this notion of either throwing away whatever the transaction did or undoing its changes or committing its changes. There have to be locks in this picture, but they are not shown. Okay, we'll get to that. Any other questions? Okay, so that's the first way of implementing transactions. Another way is actually what are called write-ahead logs. Okay, so in this case, you don't have a copy of the database to make changes to. Transactions make changes live to the original database. Okay, so the database is modified actively by transactions, and every time you make a change to the database, you write an extra amount of information to a special file called a log, saying this data was changed from this value to that other value. Okay? So you keep track of the exact changes the database, the transaction made to the database in a separate file called a log. Okay? Now, if the transaction is successful, there's nothing to do because the changes have already been made. Okay? Because the changes are being made live to the database. Okay? But on the other hand, if you want to undo the transactions changes, then you actually have to go to the log, and then you have to do what's called a replay of the log backwards, as we'll see in an example, which is also called a rollback. Okay? So if there's an abort, you read the log records and you undo the changes. Because you kept track of every change that was made, you can undo those changes. Okay? So there are two different ways to doing things. In one case, you don't make changes to the actual database, you make a changes to the copy and then merge. In another case, you make changes live to the database, but you track what changes are made so you can undo those changes. Okay? Either of these two will work. Okay? Commit needs to be atomic, and we'll come back to that when we come to locking, but let me show you an example. Okay? Your question? Yeah. Okay, good question. Question is, how do you do log rotation if the log files gets too large? That's your question, right? So log rotation is simply an approach where once the log grows to a certain amount, you can go back to the beginning and write it so it just doesn't keep growing in an unbounded fashion. Okay? In this case, log rotation is not a problem because once the transaction commits, the entries in the log of committed transactions are not of any use to us because there's no need to undo anything once you commit. So only the log entries of live transactions that are in progress are the ones we are concerned about. So you can go back to the beginning and overwrite old transaction data because those transactions are long committed. We don't care anymore. Okay? So, but good question. All right. So example. Okay? So here is a very trivial example. Our database has two values, X and Y. Okay? Very simple toy database of two values, and there's a transaction here that's going to increment X and is increment Y by 2, and then is going to do Y squared and write it to X. Okay? Again, a very trivial example, but let's try to work through what happened. Okay? So So essentially, this transaction is now going to make live changes to values of X and Y. Okay? Rather than make a copy of X and Y and making changes in private workspaces, we are going to make live change. So in the first instruction executes, the value of X is going to go from 0 to 1. Okay? You write an entry in the log saying X was modified, the old value is 0, the new value is 1. Okay? That's your log file. Okay? Then you execute the next instruction, you write another entry, okay, saying that the value of Y was 0, it has now been modified to 2. So that's what that statement did. Okay? And then you do a third statement, and then you say X was 1, it went to 4. Okay? So at this point, okay, you can still undo the transaction changes. Okay? How are you going to do this? You basically look at the log entries. Remember now, X is 4 and Y is 2. So the values of X and Y have changed from 0 to 1 and 4. Sorry, it's 2 and 4. Okay? But the way we undo this is you actually go through the log backwards, okay? And you essentially undo everything that was done by this transaction. So what you will do, if you want to undo all of those changes, is you will basically look at the last statement here. You'll say X is 4, change it back to 1. Okay? You go back to the previous statement, say Y is 2, change it back to 0. Then you come back to the first one, saying X is 1, go back to 0. Okay? At that point, you recovered X and Y back to 0. Okay? So that's how you can undo it. If you commit the transaction, there's nothing to do. You already got the final values of X and Y. You just continue from that point. Okay, of course, you have to write the transaction ID in the log. The log is one file shared by multiple transactions. Okay? I didn't show the transaction ID because you can't just replay the log backwards and undo changes of other transactions. You're only undoing one transaction. Okay? So you have to write the transaction ID and you only undo those changes, not other transaction changes. Okay, yes, question?
How does
Yeah. Okay, question is, how does a transaction know whether it's aborted or not? There are two ways you can abort the transaction. Okay, one is through explicit statements in the transaction itself that the user wrote, saying if this condition is true, abort the transaction. So here is our airline booking example. It says if one of the segments, the flight is full, abort the transaction. Okay, so that's what the user wrote. Okay, so if this condition becomes true, saying you cannot reserve this segment, then you are going to say abort the transaction. That will actually abort the transaction. Okay? So that's an explicit abort that the user put as part of error checks within the transaction code. Okay, so that's one. Okay, the second, as we will see, is essentially locking. Okay? We haven't gotten to locks yet. I haven't shown you how locking is going to work. But if there are locks and the locks cause conflicts, also the lock manager of the transaction system will abort the transaction, saying that the transaction has touched some data that it should not have touched. You should abort the transaction for safety. Okay? So the transaction doesn't do it. It's either the user code triggers it or the transactional system sees that there is a potential conflict and it will essentially abort it. Okay? All right. So essentially, that's our write-ahead log. So we've seen two approaches. Both of those approaches, as we'll see, work in a distributed world as well, as we'll get to. But you need to bring in locks and other things as well. And that's what we are going to look at next. Okay? So that brings us to concurrency control. Okay? Again, this is a term that you actually hear in databases, but it's equally valid in distributed systems. Okay? What does it mean? Okay? What does concurrency control mean? Concurrency control essentially says that you should allow multiple transactions to execute in parallel, okay, but still have the database left in a consistent state. Okay? Because one way you can say, I want to keep the database consistent, is I put a lock. Okay? That's what you did for your lab. You had threads and threads grabbed lock. But now imagine what happens if you grab a lock on the database. You have two transactions. Okay? Each transaction says lock the database. Okay? You lock the database and the transaction executes. Okay? And then the next transaction gets the database and it executes. Okay? And maybe there's a third one and it executes. So what is actually happening in this case? Locks are causing the transactions to execute one at a time. Okay? So there's no concurrency. Locking is giving you exclusive access to the database. Okay? The throughput of your system is going to decrease if you actually implement this type of lock. Okay? Because in this case, only one transaction can execute at a time. That's a transaction that holds the lock on the entire database. Okay? But imagine that this is an airline. Okay? Hundreds of users are trying to book a ticket. Okay? If the database was locked by each user to book their ticket, and everybody else is just waiting for their booking to complete. Okay? That's going to increase the time that users wait and drastically reduce the throughput of the system. Throughput is the number of active transactions that are completing, and not active use transactions that are finishing per unit time. Okay? So you don't want sequential execution. Okay? Locking will give you that, but that's not what we want in a real system. We want to allow concurrency. We want to allow multiple transactions to execute at the same time. Okay? We want the concept of lock, but we don't want the lock to provide a transaction with an exclusive access to the database. So multiple transactions can execute, yet if you have ACID properties, it doesn't matter. It looks like the transactions executed sequentially, even though they all executed in parallel. Okay? So you'll get the same effect as if you grabbed a global lock on the database, but now multiple transactions can all execute at the same time. But the transactional system is guaranteeing that the state you end up with looks like they executed one at a time, even though they actually did not. Okay? That is what concurrency control gives us. And this is what database literature will also, or textbooks will also show you, that you can't really execute only one query at a time in a database. That just doesn't work. It will slow down the entire system. There's no concurrency at all left in the system if you allow that. So you want really to achieve some concurrency. Okay? The question is, how are we going to do this? There are many techniques that we look at. Okay? They all use locks in some shape or form, but not a global lock. Okay? Take a global lock on the database, doesn't work. Okay? Instead, we'll use fine-grained locks. We'll take a lock on each data item at a time, not on the whole database. Okay? But if you take locks on individual items at a time, you may actually have conflicts that you don't want to happen. Okay? Because you take a lock and some other transaction has just modified that data, and you end up with some inconsistency. So you want to avoid these types of conflicts when you have fine-grained locks. These conflicts didn't occur when you had global locks, because you had the entire database exclusively to that transaction. Nothing else could modify it. Now our locking is more fine-grained. Okay? Different transactions are modifying different parts of the database all at once. You don't want them to make some conflicting changes. Okay? So you want to track this and then avoid it if you can. Okay? And so how to do that, we'll see. But this picture, by and large, shows us what a transactional system looks like. It is layered. Okay, so there are three components. There's a transactional manager at the top that essentially tracks begin and end transactions. And it says, should I commit or undo? So that's happening at this level. So our workspace and undo logs are all handled at that level. There's a scheduler below. Okay, that scheduler is the one that's actually getting locks on data items that a transaction is modifying. Okay? Notice that when you wrote the transaction code, user didn't say anything about locks. Okay? You just said, make a booking from here to here. You didn't say, grab a lock on this record and do something. The transaction manager will work with the scheduler, and the scheduler will say, to make these changes, it needs to get locks first on whatever item of that database is being modified. So it will grab locks for you automatically as you touch each data item. Okay? And then there's the data manager. That's the one that's actually reading or writing data to disk. Okay? So these two are the ones we are more concerned about. That's just regular file system IO. Okay? So that's a centralized transaction manager, okay, in a concurrency control system. Okay? Here's the distributed version of it. Okay? Looks very similar. Okay? Now our database is split across three machines, A, B, and C. Okay? But there's still our transaction manager. Transactions are coming in. Okay? And then there's a scheduler on each machine that is going to grab locks or whatever data is stored on that machine if the transaction touches that data. Okay? And then there's a data manager here that's reading or writing information. Okay? So that idea that we talked about of a transactional system actually generalizes to a distributed world. Okay? We still haven't seen how to get locks and get concurrency. That's something that we'll talk about in just a moment. This is just what the system looks like. Okay? The question is, what should be in the scheduler for us to get concurrency? Okay? That avoids getting global locks and making the transactions run one at a time. That's what we'll look at next. Okay, correct. So to do that, first we got to go back to this concept of serializability that we talked about in the ACID case. Okay, that was essentially the I property, isolation or serializability. Okay, so what does serializability say? Serializability says even if the transactions are executing in parallel, it should look like they executed one at a time based on the end state of the system. Okay, so you look at the beginning state, look at the end state, okay, and you ask, could these transactions have been executed in some order? Doesn't matter which order, some order one at a time, making it look like they had a global lock on the database, and can you end up in that end state? The answer is yes, you are in a consistent state, and your transactions, although they ran in parallel, are actually serialized from a database standpoint. Okay? And we'll see some examples to ask, is this a valid order or an invalid order from a serializability perspective? Okay, so again, we have three transactions, toy transactions in this case. Okay, also there's only one variable in the database, X. The database of one item. Okay, very simple. Okay, transaction 1 increments it by, first it resets it to 0, then it increments it by 1. Transaction 2 resets it 0, increments it to 2. Transaction 3 increments it to 0 and then resets it to 0 and adds 3 to that variable. Okay, so these are three transactions. Okay, if you had a global lock, okay, one of them would execute first, the second one would in some order, another one would execute next, and the third one would execute third. Okay, and whichever one executes last, if you look at the way the transaction is written, each of them just resets the state of X, okay, and then just writes its value to it. Okay, whichever one execute last will determine the final value of X. Okay, if this one went last, okay, X will end up as 3. Okay, if this one went last, okay, X will end up as 1, and then if the middle one, you will end up with 2. Okay, now we are going to let them run in parallel. We are not going to run them sequentially because we want concurrency. Okay, when you run them in parallel, these 6 statements get interleaved. Okay, they will run in some arbitrary order which we don't control. Okay, and what we want to ask on this slide, okay, the example is, are we in a consistent state, and where those transactions serialized, are they serializable even though they ran in parallel? Okay, so we'll see there are 3 interleavings. It's called schedule 1, schedule 2, and schedule 3. And we want to look, and this is the order in which schedule 1 executed those 6 instructions. That's the second one, and there's a third one. And we want to ask, what is the final state, and is it going to give us a consistent state? Is the question clear? Okay, so let's look at the first interleave. Okay, you don't really need to worry about it, but this one is actually taking the first transaction, the second transaction, and the third transaction. Okay, so you're going to end up with X is equal to 3 in this case. Okay, so the question is, so basically you started with some X and you ended up with X equal to 3. And we got to ask the question, can those 3 transactions execute in some order that ends up with X is equal to 3? Is that yes or a no? What do you think? Okay, the answer is yes, because you could have run them as A, B, and C. That will give us X is equal to 3. You ran them sequentially for that. So this interleaving is valid. You'll say this is fine. You'll take it. Okay. Here's the next one. Okay, this one does X is equal to 0, X is equal to 0, then it increments X is equal to 1, and then it runs this one, X is equal to 3. Okay, and it resets X is equal to 0, and then gets us X is equal to 3. So we ended up again with X is equal to 3. Okay, and we say, will this give us is this a valid interleaving? Okay, again, the answer is yes. Now you will see that the statements are more interleaved than the first schedule. Okay, but we started with something consistent, we ended with something consistent, so we'll take it. Okay, and here's the last interleaving where you did X is equal to 0, 0, then you did X is equal to X plus 1, you went with X is equal to 0, then you do x plus 2, x plus 3. This gives us x is equal to 5, this interleaving. Okay? And we ask, is there an interleaving possible that gives us x is equal to 5? Okay? So you will see that no matter which order you execute this in those transactions, could be A, B, C, B, A, C, C, A, B, you pick whatever order you want. We try all possible order. There's no ordering that will give us x is equal to 5 in this case. Okay? Because if you actually look at the transaction, each of them resets the value of x to 0. So the last one will either set it to 1, 2, or 3. You'll never get x is equal to 5. Okay? So this interleaving is invalid. This is not a serialized interleaving. Okay? So if you end up in this state, okay, you have to undo the transaction because they did something wrong. Okay? You shouldn't even end up in this state if the concurrency control does the right thing, but this is just an interleaving for an example's sake. Okay? Question, yes. Yes, good question. So here's one like that here in the middle of this schedule. Okay, so the question is, in schedule 3, if we had just swapped these two statements, right? So you put x is equal to x plus 2 and then x is equal to x plus 1. Okay, and you ask, is that a valid interleave? Okay, in this case, we'll take it because you did have a serialized, even though that does not look like transaction should do that, because when you're interleaving them, you will never actually get when you do them sequentially, you will never get those two statements one after the other. But from our perspective, it doesn't matter. We only care about the end result. Okay? You started with a consistent state. If you did x equal to x plus 2 and then you did x equal to x plus 1, fine. This leaves us with x equal to 3. Okay? We can find an ordering that gives us x is equal to 3. That's fine with us. Okay? So you will see that is why concurrency control is a little more complicated. It's not simple execution of sequential instruction in some order. Some interleaving still, although they don't look valid, they still give us a consistent state, and we will still accept that as a serialized schedule that works for us. Okay? And the opposite is also true, which is in the middle here, you have these two statements that never actually go together. So you ended up in a state in the middle where you have only two transactions that started. You ended up with x is equal to 3 for the first two transactions. Okay? But because the third transaction goes after this, it brings you back to a consistent state. But you will still take that because we took the beginning and the end. Even if in the middle you went off with a state that you would not normally expect, if you come back to consistency, it will still take. Okay? Normally, if you put locks and so on, this doesn't happen. But this is just a toy example to introduce the subtleties of serialization. Is this clear? Okay. All right. So now, in this case, we will actually, when we're talking about concurrency control, the two types of conflicts we want to worry about are called read-write conflicts and write-write conflicts. Okay? Read-write conflict says that some transactions already read a variable and then another transaction modified it, but that transaction is still running and it thinks there is and it's using an outdated value of the variable because you already modified it using another transaction. Okay? A write-write conflict simply says that one transaction overwrites another one. That was the example on the first slide, where one client overwrote client to overwrite client one's result, and the balance for account B was inconsistent. Okay? So we want to worry about both of those conflicts. Okay? There's no such thing as a read-read conflict. When you read data, there's no conflict. There's only a conflict when somebody reads it and then you write it, or you overwrite somebody else's changes. Okay. All right. So we'll start with a very simple concurrency control technique, okay, which is called optimistic concurrency control. Okay. And then we'll see the analog of it, which is called pessimistic concurrency control. Okay. So let's start with optimistic concurrency control. In optimistic concurrency control, there are no locks. Okay. We just let the transactions run in whatever order they want. Okay. And then we basically check at the end of this execution, okay, is the transaction in the database in a consistent way or not? It would be almost like this. Okay. There are no locks. We just let the transactions run. There's some interleaving. At the end of this, we ask, is this a consistent state? Is this a serializable schedule? Okay. The answer is yes. Okay. We just take it. You don't worry about it. If the answer is no, then you go and undo all the transaction changes. Is this clear, what I just said? This is called optimistic concurrency control. So you don't put locks at all in the data. There are no locks. Okay? We just let the transactions execute. As they're committing, we ask, is this a consistent state? Okay, because other transactions are also writing. So you want to make sure you go from one consistent state to another. If the answer is yes, you let transactions commit. Okay? The reason this works well is conflicts are actually rare in large databases. Different transactions work on different parts of the database. If you're working on two different parts of the database, there should not be a conflict. Okay? If you go back to the airline booking, if you are booking a ticket, let's say to go to Delhi, somebody else is booking a ticket to go from Chicago to, let's say, Los Angeles, those two transactions are not going to conflict because you're looking at completely different flights altogether. Okay? So when this is the case in large databases, different users and their transactions are touching different parts of the database, conflicts will be rare. So most of the time you will end up in a new consistent state and you did away with the locking over it. Okay? But when you detect a conflict, you got to actually undo the transaction. Okay, yes, question. Yeah, the question is if there are two transactions that leave the database in a consistent state, will you have to rerun them? So what happens is you abort the transaction and then you resubmit them to the database and you rerun. Right? So it's almost like you sit in the while loop saying while transaction doesn't succeed, repeat, and then once it succeeds, you're done. So, okay, question is if it's the same two, will it not succeed ever? Okay, so the reason they did not succeed is there's some interleaving based on how the CPU scheduler ran them. Okay? CPU scheduler might run things in arbitrary orders. It doesn't mean that they will always run with that interleaving the next time you run them. Okay? Because the scheduler might do things in a slightly different manner. So that's the reason they may not always conflict. All right. So the idea with optimistic concurrency control is it works well with private workspaces. Okay? Because you already saw how to do private workspaces. Let a transaction run. It makes changes to its copy. We check if it's consistent. Okay? If that end state is consistent, you merge it back. You're done. Right? So it's easy to implement with private workspace. Okay? Some pros and cons. Advantage of optimistic concurrency control: no deadlocks. Deadlock-free system. Is that clear why? There are no locks, so there can't be deadlocks if there are no locks, right? So there are no locks or no deadlock, right? Maximum parallelism, because there is no locking, there's no blocking. Okay? Transactions just run. Okay? They run at full speed. Okay? Because there's nothing to block on, because you're not trying to grab lock. Okay? Disadvantages: if the transaction aborts, you got to rerun it. Okay? And furthermore, the probability of conflict actually goes up as the load goes up. Okay? Because as the load goes up, there are more transactions in the system. The probability that any two of them touch the same data item and cause a conflict starts going up. Transactions are operating on different parts of the database. There's no conflict to begin with. But as the load goes up, the chances that two of them will conflict will go up. Okay? So that's a disadvantage. Okay? So despite the simplicity of optimistic concurrency control, many systems actually don't use them. Okay? And the reason is, as I said, how the system works actually is load dependent. At low loads, okay, the success rate of transactions is quite high. At high loads, the failure rates of transaction becomes high because more of them start conflicting. So that the database is actually doing a lot of work, but the number of transactions that are finishing is actually dropping. Okay? This is called good put as opposed to throughput. Good put is a number of transactions that actually finish, not the ones that are running. Okay? There may be lots of them that are executing, but only a small fraction finish, okay, which is not what you want at a high load because you're wasting a lot of resources, CPU resources and IO resources. So commercial systems don't implement optimistic concurrency control because of the potential of high abort rates of transactions at high loads. You would rather just have a little bit lower throughput and finish more transactions than do this. That is their reasoning as to why they don't. But it's still a good idea. Okay? You can use it if you have a lightly loaded system. It's actually good from your perspective. Okay? Now we'll look at pessimistic concurrency control. which gets us to this technique called two-phase lock. Pessimistic concurrency control has to use locking. Okay? That's how you are actually going to avoid transactions aborting because of conflicts to begin with. Okay? In optimistic concurrency control, there are conflicts and then you undo them. In pessimistic concurrency control, okay, you have to grab locks in a way that you will actually not get conflicts to begin with. Okay? And the idea is the following. Okay? The scheduler is whenever you touch a record or a data item in a database, okay, when the transaction touches it, the scheduler first goes and grabs a lock on it before you do anything. Okay? You're not locking the whole database. You're locking, let's say, it's like if you think of a database as a large Excel spreadsheet, okay, you're locking rows of the database. You're locking individual rows that they are actually being accessed by your transaction, okay, not the whole database. Okay? But in doing so, you got to make sure there are no conflicts. Okay? So what does a conflict mean? Okay, data, essentially, if you're making an operation on data item X, okay, and that data item X already has essentially an existing lock on it, then you're going to delay the transaction because somebody else has a lock, so you got to block. Okay? Okay, otherwise, you're going to grab a lock on it and you're going to essentially modify it. So you will basically keep, as you touch different parts of the database, you'll keep getting locks on whatever you have touched, and then you will hold locks on all of the items you modify, not the whole database, only the items in the database you modify or you read. Doesn't matter, you don't have to modify them, but just read or write, and then you keep going. Okay? So why is this called two-phase lock? The rule in this locking scheme is this: once a lock is essentially granted, okay, and you can keep acquiring locks, okay, until you, at a point where once you start releasing locks, you cannot acquire them again. Okay? So essentially, if you look at how the database executes, there's what's called a growing phase where you keep getting more and more locks as the transaction touches more and more data items. And once you're done with the data item, you're not going to use it in the rest of the transaction. You can release a lock. But the rule is once you start doing a release, you can only do releases from that point until the end of the transaction. No more grant or acquiring locks. Okay? This is why it's called two-phase locks, because you will see this picture. Okay? So this is a picture of how many locks a transaction holds at any given time. Okay? X-axis is time. Okay? And Y-axis is the number of locks. The first time you touch some data item in the database, you grab a lock. And you touch another data item, you grab another lock, and the third one, the fourth, and so on. And you'll see at this point in time, okay, all the data items you got to touch have been touched. Okay? So then the scheduler can start releasing locks, but once you release, you cannot get any more locks. Okay? So you have to wait until you are sure that the transaction will not touch any new data items in it. And at that point, you can start releasing, and then as you're done with each one, you can start releasing. This is the shrinking phase. There's a reason you actually do this, because it actually gives you some properties, because if you don't get locks in the right order, you're going to get a deadlock. Okay? This should be clear, okay, from this trivial example that you probably have seen before when you studied locks, which is, let's say there are two threads that are trying to get locks on A and B. Thread A gets a lock on A and tries to get a lock on B. Thread B gets a lock on B first, then it tries to get a lock on A. But if each of them get the first lock, then they block on the second one and you're dead. Okay, that's a very standard deadlock model. So if you do the same thing in two-phase locking, your two transactions, one has a lock on A, it's waiting for B, but B is held by the second transaction, which is waiting on lock on A, and you're done. These two transactions will dead. Okay? So you got to be careful in how you grab locks in the transaction to prevent these deadlocks. So you have to order the locks and so on, which will give you deadlock-free properties. Okay? The other thing that you want to do is simplify the shrinking phase by saying that you basically have a growing phase, and the shrinking phase is when you commit, you release all the locks at once. That also further simplifies when you release locks and so on. Okay? Otherwise, you may release a lock, some other transaction might then come and modify it, and that might cause some conflict at some later time. Is this clear? How you can actually grab locks? And so the basic idea is whenever the transaction touches a data item X, you got to get a lock. The lock is in use, the transaction is going to wait. Okay? This is where the parallelism will be lower than in the optimistic concurrency control. But it's still better than grabbing a global lock, okay, which means only one transaction can run it. Here, at least multiple can run depending on which locks they are holding and so on. That clear? Okay. All right. So that's our two-phase locking, also called 2PL. I have one more technique, which is timestamp based concurrency control, and then we'll be done with concurrency control. Okay. So again, here we are not going to actually use locks. Instead, we are going to use timestamps to tell us which transaction to allow to commit and which one to abort. Okay. This is where you will understand where you have read-write conflict and write-write conflicts very clearly. Okay. So the idea here is each transaction is going to be given a timestamp. That's the timestamp it starts. Okay. It can be a logical timestamp, it can be a physical timestamp. That doesn't matter, but you basically have a timestamp which is your start time. Okay. Now, when a transaction Ti wants to do an operation on some data item, and then Tj has also made an operation on that data item, you are going to essentially have to abort the transaction if your timestamp is lower than the other transaction. That means that a newer transaction has already modified or done something to the data item. That's a conflict. Okay. You are an older transaction that's still modifying something. Some new transaction has come along, has modified it, so you abort the transaction. Okay. That's the basic idea. And if you abort the transaction, you must restart it with a larger timestamp. Okay. And the question is, how are you going to make this check very explicitly? The way we will do it, for every record in your database, you will maintain two timestamps. Okay. The transaction itself has a timestamp, but every record in the database also has a timestamp called a read timestamp and a write timestamp, or a max read timestamp and a max write timestamp. The max timestamp of a data item X is the max time, is essentially the most recent transaction that essentially touched it, read it. Okay. And the write timestamp is the timestamp for the most recent transaction that wrote to it. Okay. So this is like the most recent read time and the most recent write time. Okay. That's what it's tracking. So which transaction has read it most recently, which transaction has returned to it most recently. That's what you're going to track. And here's a very simple way your read and write operations will work and tell you whether your operation will succeed or you got to abort. Okay. So for read of X, you will check the transaction times. If the transaction timestamp is less than a max write timestamp, then you abort. That says you are trying to read a data item, a newer transaction already written to it. Okay, that's a read-write conflict. Okay? So you are reading a data item that's already been modified by someone else with a newer timestamp, because the max write timestamp is actually greater. Then you essentially abort. Otherwise, you perform the read and update the read timestamp to be the current max RTS and this. So you update it if you are a newer transaction. Okay? And then you essentially have a write operation. So you say if the timestamp of the transaction is less than the max read timestamp or less than the max write timestamp, you will abort. Okay? Because what this is saying is you are trying to write to a data item, a newer transaction is already read. That's a read-write conflict. Okay? Or you're trying to modify a data item that someone else has already modified. That's a write-write conflict. Okay, so you see, is there a read-write conflict or a write-write conflict? In either case, you'll abort the transaction. Otherwise, you'll perform the write and update the max write timestamp. Okay, so what we are doing now is we are tracking for every data item. When was it last read? When was it last written? And also tracking the most recent transaction that read or write it. And if someone is older is trying to read or write to it, you abort. That's the basic idea. Okay? Only the newest transaction is actually allowed to complete. Yes, question. Okay. If you're writing, why are we considering the read and why not only consider the write? Right? That's a good question. So essentially, when you're trying to write, you want to make sure that nobody has actually read it and is using that to calculate something, because you want to make sure whatever any other transaction is using for this data item is the most current value. Okay? So if you're about to modify it, then that transaction will now have an older value of that data item and it's still a transaction in progress. So you don't want to do that. You want to be the newest transaction to modify. Yes.
Won't this result in starvation of longer transactions?
Won't this result in starvation of longer transactions? Won't result in a starvation if it is the case that the transactions are modifying the same data item and some of them are long running, the shorter ones will keep winning. You're right. Okay? But this assumes that if you have a balance of smaller transaction, bigger transaction, lots of data items, you will essentially not have that. Okay? Otherwise, you have to go to pessimistic concurrency control, where you actually have to have locks. That's the only way to guarantee. Any other questions? Okay, there's an example here which is showing the same thing. I'm going to ignore that, but I just want to do a quick recap of concurrency control. Okay? The basic idea was you want to essentially have the notion of locks and the notion that transactions executed sequentially, but you want to let them execute in parallel. Okay? This is something you don't do in threads. By threads, when you grab lock, only one thread executes at a time. You don't let multiple threads change some data item and then say later on, let's see if this is consistent or not. That's okay when you're threading, but in databases, that's actually going to slow down the performance. So you want concurrency, but you want to make it look like things are executing sequentially, even though they're executing concurrently. For that, we looked at optimistic concurrency control and pessimistic concurrency control. Each one has its own pros and cons in terms of having locking overhead, but not having a lot of aborts, versus having no locking overhead, but potentially higher failure rates at higher load. Okay? So these are the two ways you can implement some of these techniques. These ideas, as I said, although we looked at it from a database or a data standpoint, they work more generally. Okay? If you want to have atomicity, all or nothing properties, similar things will actually work for you. Okay? So when you have large applications that will have the notion of transaction, these are some of the ideas you can apply to those larger contexts. All right. So we'll end it here today, then continue next time. All right.